Okay. It's been a long day. We are still on section 1, theory of heat, page 32. Here we go. Pound of clean, dry air has a total volume of 13.33 cubic feet at standard atmospheric conditions. Its specific volume would then be 13.33 cubic feet per pound. As air is heated, it becomes lighter and its specific volume increases. As air is cooled, its specific volume decreases. Hydrogen has a specific volume of 179 cubic feet per pound at standard atmospheric conditions. Because more cubic feet of hydrogen are needed to make a pound, it has a higher specific volume. Thus, it is lighter than air. Although both are gases, the hydrogen has a tendency to rise when mixed with air. Natural gas, which is a popular fuel used for heating, is also lighter than air and has a tendency to rise like hydrogen. Propane gas, another frequently used heating gas, has to be treated differently than natural gas because it is heavier than air. Propane has a tendency to fall and collect in low places and poses a danger in the event it ignites. The specific volume of propane gas is 8.62 cubic feet per pound, and the specific volume of natural gas on average is about 22 cubic feet per pound. Note, the specific volume of natural gas will vary based on the makeup of the gas. Unlike propane, which is a compound, natural gas is a mixture of different hydrocarbons. The typical range of specific volume for natural gas is between 15 cubic feet per pound and 24 cubic feet per pound. Specific volume and density are inverses of one another. This means that specific volume equals 1 divided by density, and that density equals 1 divided by specific volume. If one knows the specific volume of a substance, its density can be calculated and vice versa. For example, the specific volume of dry air is 13.33 cubic feet per pound. Its density would then be 1 divided by 13.33 cubic feet per pound equals 0.075 pounds per cubic foot. Notice that the units are inverses of each other. Substances with high specific volume are said to have low densities. Also, substances with high densities have low specific volumes. Since density and specific volume are inverses of each other, multiplying the density of a substance by its specific volume will always yield a product of 1. The specific volume of air is a factor in determining the fan or blower horsepower needed in air conditioning work. As an example, moving air that has a low specific volume requires a blower motor with higher horsepower, while moving air that has a specific volume can be accomplished with a blower motor with a lower horsepower rating. The specific volumes of various pumped gases is valuable information that enables the engineer to choose the size of the compressor or vapor pump to do a particular job. The specific volumes for vapors vary according to the pressure that is exerted on the vapor. As the pressure of the gas increases, the specific volume of the gas decreases and its density increases. As the pressure of the gas decreases, the specific volume of the gas increases and its density decreases. The graph provided in figure 2.6 graph showing the relationship among pressure, specific volume, and density. Give you a look at that. Shows the relationship that exists amongst pressure, specific volume, and density of gases. The horizontal scale across the bottom of the graph represents pressure and increases from left to right. The vertical scale on the left side of the graph represents specific volume and increases from bottom to top. The vertical scale on the right side of the graph represents density and decreases from bottom to top. Consider a gas that experiences an increase in pressure from A to B, figure 2.7. Pressure increases from point A to point B. Extending these lines upward until they cross the curve identifies two additional points, A degrees and B degrees. Figure 2.8, identifying points A degree and point B degree on the curve. Drawing horizontal lines from points A provides 2 points, namely A. I don't know what it means. It has like asterisks. Do I say degrees? And then they have like way more on the next ones. Figure 2.9, as the pressure of the gas increases from A to B. It can be seen that the specific volume decreases from A asterisk asterisk to B asterisk asterisk, where B asterisk asterisk is lower than A asterisk asterisk. It can also be seen that the density increases from A triple asterisk to B triple asterisk, where B triple asterisk is greater than A triple asterisk. I gotta figure out. The concept of specific gravity, as discussed in section 2.4, can also be applied to gases. Just as the density of water was used as a baseline to calculate the specific gravity of liquids and solids, the specific volume of air can be used as a baseline to determine the specific gravity of gases. As mentioned, the specific volume of air at standard atmospheric conditions is 13.33 cubic feet per pound, so the specific gravity of air is 1. Since 13.33 cubic feet per pound divided by 13.33 cubic feet per pound equals 1. Hydrogen with a specific volume of 179 cubic feet per pound. Similarly, the specific gravity of propane gas is 1.6 brackets times 13.33 cubic feet per pound divided by 8.62 cubic feet per pound, close brackets. And the specific gravity of natural gas on average is 0.6 brackets times 13.33 cubic feet per pound divided by 22 cubic feet per pound, close brackets. In general, gases with specific gravity values less than 1 are lighter than air, while those with specific gravity values greater than 1 are heavier than air. 2.6 Gas laws. It is necessary to have a working knowledge of gases and how they respond to pressure and temperature changes. Gas laws have been developed to aid in the understanding of the reaction of gases and the pressure, temperature, volume relationships in various parts of an air conditioning or refrigeration system. Whenever using pressure or temperature in an equation like the gas laws, one has to use the absolute scales of pressure, psia, and temperature, Rankine or Kelvin, or the solutions to these equations will be meaningless. Absolute scales use 0 as their starting point because 0 is where molecular motion actually begins. Boyle's law. In the early 1600s, Robert Boyle discovered that when pressure is applied to a volume of air that is contained, the volume of air becomes smaller and the pressure greater. Boyle's law states that the volume of a gas varies inversely with the absolute pressure, provided the temperature remains constant. For example, if a cylinder with a piston at the bottom and closed at the top were filled with air and the piston moved halfway up the cylinder, the pressure of the air would double. Figure 2.10. Absolute pressure in a cylinder doubles when the volume is reduced by half. That part of the law pertaining to the temperature remaining constant keeps Boyle's law from being used in practical situations. This is because when a gas is compressed, some heat is transferred to the gas from the mechanical compression, and when gas is expanded, heat is given up. However, this law, when combined with another, becomes practical to use. Okay, that's 2 pages. Page 32 and 33. Thanks for tuning in. I will see you tomorrow.